Welcome, everybody. It's my pleasure today to introduce Sunhyuk Lim, and he'll be telling us about the Gromov-Hausdorff distance between spheres.
Okay, thank you, Emily. Before starting my talk, I want to advertise some event. So there will be a workshop called Bridging Applied and Quantitative Topology Workshop, organized by me and John Bush, Facundo, and Henry. And this workshop will be held in most likely next year, May. And topics include such as Beatrix complex filtration, filling radius, Gromov-Hausdorff distance, persistent homology, cohomology, but of course it is not limited to those things. And if any of you have any question, please send us an email with this email or Henry's email. Okay. Sorry, that's important information. Is it online workshop? Okay, so let's start. Today, I want to talk about the Gromov-Hausdorff distance between spheres. And this is a joint work with my advisor, Facundo Memoli and Zane Smith. So let's start. Gromov-Hausdorff distance is a distance on the collection of compact metric spaces. And despite being widely used in Riemannian geometry and now topological data analysis, but the precise value of Gromov-Hausdorff distance between two spaces are largely unknown. And hence, the goal of this project is computing some estimates of Gromov-Hausdorff distance between m-dimensional sphere and n-dimensional sphere, where m and n are between 0 and infinity. And in this project, m is always smaller than n, unless I state otherwise. And why do we care about? Because n-sphere plays a role of model space having one n-dimensional hole, and hopefully this theoretical result will be a reference for the other computations. In other words, to summarize, we want to fill this matrix of Gromov-Hausdorff distance between m-sphere and n-sphere. And today I will summarize one of the important results in this project. Some of the important results in this project. Okay, so now let's set up some preliminary things. Given two sets x and y, a correspondence between them is any relation R. In other words, it is just a subset of x times y, such that pi sub x of R is whole x and pi sub y of R is whole y. Here, of course, pi sub x and pi sub y are just canonical projections to x and y, respectively. And the calligraphic R of x comma y will denote the set of all correspondences between x and y. Moreover, for any relation R, when x and y are metric spaces, one can define the distortion of R in this way. Of course, d sub x is a metric for x, and d sub y is metric for y. And one remark is that for any map phi from x to y, a distortion of phi indicates the distortion of the graph of map phi, because we can see graph of phi as a relation between x and y. And in particular, if phi is a surjective map, the graph of phi becomes correspondence. And in this project, many correspondences we built actually have this kind of form, comes from map. Finally, here's the definition of the Gromov-Hausdorff distance. It is just 1/2 times infimum of over all the possible distortion of correspondence between x and y. And there are other equivalent definitions for Gromov-Hausdorff distance, but in this project, we will use this one, this version. And with the above characterization of Gromov-Hausdorff distance, it is easy to check that actually Gromov-Hausdorff distance between Sm and Sn is always upper bounded by pi over 2 for any m and n between 0 and infinity. It is actually a result of more general lemma saying that the Gromov-Hausdorff distance between x and y is upper bounded by the maximum between diameter of x and diameter of y. And of course, the diameter of m and n spheres are all pi, so we have this result. Okay. So far, so good? Okay. So now let's jump into our original work. One thing I want to emphasize in this project is that to compute the lower bounds of the Gromov-Hausdorff distance between m sphere and n sphere, topology plays an important role, while computing upper bounds is mostly related to geometry. And here is an example. If we use persistent homology and the stability of the Borsuk distance, we have this inequality. Consider m-dimensional sphere and n-dimensional sphere, and m is lower integer less than n. And by the stability, the Gromov-Hausdorff distance between Sm and Sn is lower bounded by 1/2 times the Borsuk distance between m-dimensional barcode of Sm and m-dimensional barcode of Sn. And there's other result in my other project, computing the interval in the barcode of spheres. We were able to compute that this 1/2 times Borsuk distance between two barcodes are actually lower bounded by 1/4 times zeta sub m. Here, zeta sub m is r cosine of -1/m plus 1. So with this technique from topological data analysis, we already have a somewhat non-trivial lower bound of Gromov-Hausdorff distance between Sm and Sn, which is this number. And by the way, there's a yes?
Sunhyuk, zeta m is this diameter of inscribed regular simplex. Is that right?
Yes, yes. I was planning to interpret.
I'm sorry.
Yeah, no.
My apologies.
So there's a way to interpret this number, zeta sub m. It is actually not diameter, but if we consider regular m plus 1 simplex inscribed in Sm, then you can consider the distance between two vertices of that m plus 1 dimensional simplex. That geodesic distance between two vertices is exactly this zeta sub m. And actually diameter, which Henry just mentioned, is strictly greater than this zeta sub m for m greater than or equal to 2. But when m equal 1, they are same. But yeah, diameter is in general greater than this number, of course. And for example, if you consider m equal 1 case, it means that you have to imagine regular triangle inscribed in S1. And of course, you consider the distance between these two vertices, and that will give 2 pi over 3. So zeta 1 is 2 pi over 3. So that is the geometric meaning of zeta m. And in this project, we were able to prove better lower bounds by using some Borsuk-Ulam type theorems. Actually, you will see that this number will be changed to 1/2. So our new lower bound is 2 times better. Furthermore, this lower bound will be tight. Okay, so let's see. First, I want to prove the Gromov-Hausdorff distance between S0 and Sn is exactly equal to pi over 2. And the Gromov-Hausdorff distance between Sm and S infinity is also exactly equal to pi over 2. To show that, the main tool is so-called Schroemann theorem, which is this. For any integer n, positive integer n, consider closed cover use of 1 that use of n plus 1 of Sn. Then there must be some use of I0 contains 2 antipodal points. So with this, one can prove the following. So let me prove this first claim. The Gromov-Hausdorff distance between S0 and Sn is actually exactly equal to pi over 2. And if you remember, a few slides before, I already showed that the Gromov-Hausdorff distance between S0 and Sn is upper bounded by pi over 2. So to prove the equality, we only need to show lower bounds is also pi over 2. Let's prove this. Fix arbitrary correspondence R between S0 and Sn. And recall that S0 just consists of 1 and -1, and their distance is pi. And one can consider set A sub minus, which is a closure of all the points x in Sn, such that -1, x belongs to this correspondence R. And in the similar way, we can also construct a set A plus, which is a collection of x such that 1, x is contained in this correspondence R. And of course, this A minus, A plus form a close covering of this Sn. And therefore, we can apply this Schroemann theorem. It means that one of them must contain 2 antipodal points. And it means that the distortion of R is lower bounded by pi. And since R is arbitrary correspondence, by the definition of the Gromov-Hausdorff distance, it implies that the GHD distance between S0 and Sn is lower bounded by pi over 2. So one can conclude this equality. So that's how we prove this first claim. And for the second claim, the Gromov-Hausdorff distance between Sm and S infinity, the proof of that fact is in the same spirit, but it requires a little bit more detail, so I will skip here. But I can discuss after the presentation if any of you want, of course. Good? Okay. So we just computed these numbers are all pi over 2 when m is 0 or n is equal to infinity. And at this step, one might conjecture that Gromov-Hausdorff distance between Sm and Sn is maybe always pi over 2 for any mn between 0 and infinity. But actually, it is not true. The situation is more interesting than that. Because we were able to prove that the Gromov-Hausdorff distance between Sm and Sn is strictly less than pi over 2 when m and n are strictly between 0 and infinity. How to prove this? We were able to prove this fact by building some special correspondence between Sm and Sn such that the distortion of R is strictly less than pi. And this construction of this special correspondence was done by using the space filling curve and suspensions. I didn't include the proof for now, but there are some slides explaining this proof at the very end of the presentation slide. So I can talk about if any of you want how to prove this fact. But now I want to focus on this low bound theorem which I promised in the beginning of the presentation. We were able to prove that when m is smaller than n, and both m and n are strictly between 0 and infinity, the Gromov-Hausdorff distance between Sm and Sn is lower bounded by 1/2 zeta sub m. And the proof is done by certain geometric version of Borsuk-Ulam theorem, proved by originally Dubins and Schwarz. Moreover, we were able to prove that actually the equality holds for some cases. More precisely, when m, n is 1,2, 1,3, and 2,3, we were able to show that the equality holds. Good? Okay. So before jumping to proof of this theorem, let me try to explain our flow of idea, why we thought that some Borsuk-Ulam type theorem is the right tool. As you already seen, we used Lusternik-Schurman theorem to prove some previous theorems. And that theorem is equivalent to the following classical Borsuk-Ulam theorem. For any continuous map G from S to the m plus 1 to the Sm, G cannot be antipode preserving. But if you remember the definition of the Gromov-Hausdorff distance, that it does not require any continuity. So it is a reasonable guess that we may need this continuous version of Borsuk-Ulam. So more precisely, the question is the following. If G is a map from S to the m plus 1 to the Sm, which is antipode preserving, then quantitatively speaking, how discontinuous is G? So to state the answer for this question, of course, we need to define some quantity measuring the discontinuity. And this modulus of discontinuity is the one we used, and its precise definition is the following one. If you have a map G from two metric spaces X and Y, we can define modulus of discontinuities in this way. But only thing you have to remember for now is just modulus of discontinuity is larger than the map G is more discontinuous. And we were able to observe that the modulus of discontinuity is actually upper bounded by distortion of map. Good? Okay, so here's our main tool. For each map, for each m, if a map Z from S to the m plus 1 to Sm, which is not necessarily continuous, and if G is antipode preserving, then the modulus of discontinuity of G is greater than or equal to zeta sub m. And therefore, by the previous observation, distortion of G must be also greater than or equal to zeta sub m in this case. By the way, there's a more succinct proof of this theorem, succinct than the original proof by Dubins and Schwarz, and the strategy is hinted in Irima Tusek's book. And we have a separate appendix explaining that proof in the paper in archive. Okay, so we need one more technical tool, which is A of Sm. For non-negative integer m, A of Sm is a subset of Sm, and it is defined in the inductive way. A of S0 is just one of the 2 points of S0, and A of S1 is union of strict upper hemisphere and A of S0. Here, we are identifying A of S0 and equator of Sm, equator of S1. So in the similar way, we can define A of S to the m plus 1 So this is A of S1, this is A of S2. And what is the property of A of Sm? They satisfy the following. If we consider intersection between A of Sm and antipode of A of Sm, which is denoted by minus of A of Sm, that must be empty set. But if you consider union of them, it must be whole Sm. So with this notion, now we can state the following technical lemma. It's simple but very useful. For any map phi from A of Sn to S to the m, the distortion of phi and distortion of map phi hat are same. But what is this? What is the map phi hat? Phi hat is the map from whole Sn to Sm extending original phi, and it is defined in the following way. If the input is x, where x is already in A of Sn, the output is just phi of x, original phi of x. But the input is minus x. In other words, if it is contained in minus A of Sn, then the output is minus phi of x. In this way, we can define phi. So one important fact you can observe from the definition is this phi hat is antipode preserving. So phi and phi hat have same distortion. Furthermore, phi hat is antipode preserving. Is this okay? And here is a picture of the construction of phi hat. By the way, as I said, in this project, usually m is smaller than n. That's implicitly assumed everywhere. But only for this lemma, it doesn't need to be. N can be smaller than m. It doesn't matter. Okay, so with the Dubin's and Schubert's Borsuk-Ulam theorem and this technical lemma, finally, we are ready to prove this Gromov-Hausdorff distance between Sm and Sn is lower bounded by 1/2 times zeta sub m. Okay, so let's prove this. Suppose not, it means that there is a correspondence R between Sm and Sn such that distortion of R is strictly less than zeta sub m. But here, we assumed n is strictly greater than m. Therefore, s to the m plus 1 is contained in Sn, hence obviously a of s to the m plus 1 is contained in Sn. Now, we build the following map phi from a of s to the m plus 1 to s to the m. That this phi satisfies for any point x in a of Sn plus 1, x comma phi of x must be contained in this correspondence R. We can make such phi because R is a correspondence. Furthermore, distortion of phi is less than or equal to distortion of R from the construction. Hence, strictly less than zeta sub m. Now, apply the distortion preserving lemma in the previous page for this map phi. Then what we get is the map phi hat from whole s to the m plus 1 to s to the m, such that distortion of phi hat is equal to distortion of phi, therefore strictly less than zeta sub m. Furthermore, phi hat is also antipode preserving. And that contradicts the Dubin's and Schubert's Borsuk-Ulam theorem, because Dubin's and Schubert result says that any map from S to the m plus 1 to Sm, which is antipode preserving, must have distortion greater than or equal to zeta sub m. More precisely, it has modulus of discontinuity greater than or equal to zeta sub m. Therefore, its distortion must also greater than or equal to zeta sub m. Therefore, this fact contradicts to this result contradicts the Dubin's and Schubert's Borsuk-Ulam theorem. Therefore, we can conclude that for any correspondence R between Sm and Sn, the distortion of R must be greater than or equal to zeta sub n. And since R is arbitrary, that is true, so we can conclude this lower bound. So far, so good? Okay.
Can I ask a question? I don't want to interrupt your flow.
Sure. No, please.
Your proof sort of begs the question if there's versions of Dubers and Schwarz where it's not for the m+1 sphere to the m sphere, but the m+2 sphere mapped to the m sphere or the m+3 sphere mapped to the m sphere. Can you get better numbers in a Duber and Schwarz when you're mapping from a sphere of 2 dimensions higher or 3 dimensions higher down to SM? Do you know anything about this, or have you thought about this?
No. Actually, that is one of the question I had, but we don't have anything specific for now. Yeah, I'm wondering that, but yeah, no, we don't have anything to tell yet.
Cool, thanks.
Okay. Yes, so, and as I said before, we know that as some pair of m comma n, this equality holds, and one of them is when m is 1 and n equal 2. So let me try to explain why that is true. Okay, so we already learned that the Gromov-Hausdorff distance between S1 and S2 is lower bound by pi over 3. So to show equality, we only need to this upper bound direction. And to do that, we will build a surjective map from S2 to S1, having distortion exactly equal to 2 pi over 3. So how can I do that? So imagine map phi from A of S2 to S1. Here A of S2 is something like, maybe it's better to, yeah, this is A of S2. And if you remember the definition, A of S2 is a union of a strict upper hemisphere and A of S1. Again, here we are identifying S1 and equator of S2. And imagine dividing strict upper hemisphere into 3 equal parts, like N1, N2, N3. In other words, each Ni will look like some spherical triangle, and their diameter will be 2 pi over 3. Now we are ready to define this map, phi sub 2, 1. Fix arbitrary point x in A of S2, and if x is contained in strict upper hemisphere, then it must be one of the Ni. Then the output will be Ui in S1. Here, U1, U2, U3 is a vertex, is vertices of some regular triangle. And on the other hand, if x is in the equator, in other words, if x is a point of A of S1, then it goes to x itself. So it is just identity on A of S1. So in this way, we can define phi of 2, 1. Then we can prove that this distortion of phi sub 2, 1 is exactly 2 pi over 3. And well, I think we have enough time, so let's see why that is true for some cases. For example, to compute the distortion, you have to compute the phi yes, you have to compute this value. Now let's do case-by-case analysis. For example, suppose x and x prime points in same n1. Then this value, the distance between phi 2, 1 of x and distance between phi sub 2, 1 of x and phi sub 2, 1 of x prime will be 0 because they all go to u sub 1, while the diameter of n1 is 2 pi over 3. Therefore, this part is upper bounded by 2 pi over 3. So we can show that this distance, this distortion is less than or equal to 2 pi over 3. And the other case is when x is n1, x prime is n2, then distance between x and x prime can be any number between 0 and pi. However, the distance between phi of x and phi of x prime will be distance between u1 and u2. Therefore, it is equal to 2 pi over 3. So again, in this case, distortion is also upper bound by 2 pi over 3. So by doing this simple case-by-case analysis, we can prove this distortion is 2 pi over 3. Then what we can do is, of course, applying the technical lemma. So we have a map phi hat sub 2, 1, which is a map from whole S2 to the S1. And that will have a distortion exactly equal to 2 pi over 3. And because of that, as we wanted, this is Gromov-Hausdorff distance between S1 and S2 is exactly equal to pi over 3. Good? Okay. So next, another case when the equality happens is when m equal 1 and n equals 3. The proof of this fact is rather complicated than the previous one, but at least let me try to sketch the construction of the map. Again, we only need to prove the upper bound case. To do that, we will build a map phi hat sub 3, 1. It is surjective from S3 to S1. Also, its distortion will be 2 pi, exactly 2 pi over 3. And here is how to build this map. For each point Q in S3, there is a certain way to choose the unique pair P sub Q and alpha sub Q. Here, P sub Q is a point of S2, and alpha sub Q is just an angle between 0 and pi. Moreover, this pair P sub Q and alpha sub Q satisfy this. What it means is the point Q is rotation of P sub Q by angle alpha sub Q. Here, as usual, we are embedding S2 instead of S3 as an equator. And we define this map H in this way. H sub Q is P sub Q, alpha sub Q. And with this map, we can define the required map phi sub 3, 1 in the following way. For each point Q in S3, phi sub 3, 1 of Q is rotation of phi sub 2, 1 of P sub Q by angle alpha sub Q. But what is phi sub 2, 1? It is the same map we used in the previous construction. More precisely, yeah, this is the one. So phi sub 2, 1 hat is the surjective map from S2 to S1 having distortion exact 2 pi over 3. And by using the same map and rotating it slightly by angle alpha sub Q, we can define this new map phi 3, 1 hat, and that is, it has a distortion exactly equal to 2 pi over 3. Therefore, and here is a picture representing how to construct a phi 3, 1. There must be had more precisely, but anyway, yes. So this is a conceptual picture, and with this result, and as we wanted, we can prove that the Gromov-Hausdorff distance between S1 and S3 is upper bounded by 2 pi over 3. Therefore, the equality actually holds. Here, one small remark is that if we consider map pi 1 composition H, where pi 1 is just a canonical projection from S2 times 0 pi to S2, then if this composition is just a surjective map from S3 to S2, then the inverse of antipodal pair Pn minus P will be actually isometric to S1 for any P in S2 outside of S1. So there is a certain degree of similarity to Hopf vibration here, and there's another Hopf vibration from, I think, for example, from S7 to S4, something like that. So maybe there's more general way to build the correspondence for higher dimensional sphere, but we haven't figured it out yet. Okay, so to summarize, we were able to compute exact value for this row and this column, and 1,2, 1,3, and we also have, we were able to build the exact value when m equal to S3. It is that is just 1/2 times zeta sub 2, but the construction of the correspondence to prove that is quite complicated and has somewhat has different structure than the others, so I didn't include it. And other than these blocks, there we were able to build some non-trivial estimates, but we don't have exact value yet. So there are quite a lot of open questions, obviously. One thing I'm most interested in is just proving or disproving this equality. The Gromov-Hausdorff distance between SM and SM plus 1 is 1/2 times zeta sub m. And we all know that that is true when m equal 1 and 2, but when m equal greater than or equal to 3, can you say it is true? So this part, can we compute exact value for that? I would be very happy if we can do that. And the second one is, for example, if we fixed m, then the Gromov-Hausdorff distance between SM and Sn is non-decreasing with respect to n. And surprisingly, this is also we don't know. I have no idea how to prove this yet. And if so, how fast that number will increase? That is another question. Next, this is one of the recent questions we discovered. Instead of using geodesic distance for SM and Sn, what if we use Euclidean distance for those spheres, L2 distance? First, we thought that probably we'll be able to, it will be just a direct translation from the geodesic case. But surprisingly, we have some evidences it's not the case. Computing Euclidean distance between, computing SM and Sn with Euclidean distance will require, probably will require another techniques. Okay, so that is all of I prepared now, and this paper is uploaded in archive, so you will be able to see the details if you want. Thank you.
Thanks so much, Sunhyuk. So before we get to questions, let's briefly unmute yourself if you like and applaud for the speaker. Questions for Sunhyuk?
Hi, Sunhyuk. Can you hear me?
Yes, hi, Eugene.
Yeah, thank you for a great talk. Can you talk a little bit more about that evidence you pointed out at the last bullet point?
Okay.
A little bit, yeah, thanks.
Sure, okay. So we were able to prove that the Gromov-Hausdorff distance between S1 and S2 is equal to 2 pi over 3 if we use a geodesic distance, right? And not only that, we were able to prove that distance between S1 and upper hemisphere. Sorry for bad hand. So this is upper hemisphere of S2, and this is S1. And actually, not only between S1 and S2, the distance between S1 and upper hemisphere of S2 is also 2 pi over 3. And what is 2 pi over 3? And sorry. It is, it is pi over 3. 1 over 2 times zeta 1. But what is zeta 1? As I said, the zeta 1 is distance between two vertices of regular triangle inscribed in S1, right? So if we make a natural guess, what if the Gromov-Hausdorff distance between S1 with Euclidean distance versus strict the upper hemisphere of S2 with Euclidean distance? The natural translation is probably it will be 1 over 2 times the distance between 2 points in Euclidean distance. In other words, square root of 3. So that was our original guess, direct translation from the geodesic case. But we were able to prove there is a correspondence between two of them having distortion strictly less than square root of 3. Therefore, it implies that the Gromov-Hausdorff distance between S1 and upper hemisphere and upper hemisphere of S2 and S1 with Euclidean distance is less than 1 over times 2 the distance between two vertices, which is not, we didn't expect it. So yeah, it seems it's more complicated than we expected. Of course, there are some relations between two of them. There's some, I don't remember which one was larger or smaller, but of course we can make some relationship between two of them, but yeah, of course this, yeah, in general, we can prove I think, sign of Gromov-Hausdorff distance between SM. Yeah, of course we can make some relation between two cases, but that's not something directly translated from the geodesic case. Yeah, that's what I meant. And it is in the last section of our newest version of the archive paper. Yes.
Okay, thanks.
Thank you.
A follow-up question while you're on this slide. So you were looking at S1 with the Euclidean metric and the upper hemisphere of S2 with the Euclidean metric. Can you, in the Euclidean case, can you still do your distortion preserving trick under antipodal maps to replace the upper hemisphere of S2 with S2, or do you not know that?
Yes, that is a good point. We have some version of the distortion preserving lemma, but that is not as good as geodesic case. So it makes some gap. That's the problem. Yeah, that's exactly the problem. Yeah.
More questions? All right, I'm going to ask another one. So Sunhyuk, if you could go back to the slide about S3 and S1. Right, so I'm trying to understand this map H. So how you take a point in S3 and assign a point in S2 and an angle. So okay. You're thinking of S2 as of course this hemisphere. What angle does that associate it to? Is that associated to angle pi over 2?
Sorry, can you clarify your question? I could understand. Yeah.
Is it correct to say that if there's an S2 hemisphere inside of S3 that all gets mapped to the same angle, maybe pi over 2, or
all mapped to the same angle?
I was wondering if you could explain this map again. Can you do the same map in the case of like S2 and S1, for example?
For S2 and S1. For S2 and S1, we can consider just the usual rotation angle.
No. Yeah. So okay. So like what angle does the North Pole get mapped to, or what angle does the South Pole get mapped to?
Okay,
You know,
okay. So I mean, so North Pole of S2 or North Pole of S3.
Yeah. Take your pick. I'm just trying to understand this. Yeah.
Okay. So if you pick North Pole of S2, North Pole of S2, and in our coordinate system, it will be represented as 0, 0, 1, 0, because we are seeing S2 as a subset of S3. And what is the inverse of this map? Okay, I remember. It is something like collection of all the cosine alpha, sine alpha. Yeah. So maybe it's better to write down. So here, the one we are using as a rotation by angle, which is T sub alpha, is just this cosine alpha, sine alpha, sine alpha, cosine alpha, and the same.
I see.
Yeah. Sine alpha. Yeah, and of course everything is true. And
I see. In both pairs of coordinate axes, you're rotating
yes.
by angle, by that angle.
Yes, because we are viewing S3 as a subset of alpha, and S1 and S2 are all embedded in S3. So we can apply the matrix multiplication, of course. So that's how we choose alpha sub q and p sub q.
So can you generalize this like as a map from SM plus 1 to SM whenever M is even?
Whenever M is even, yeah, I think so. Yeah, of course we can imagine the similar construction for that cases, but I don't know how to track distortion. Yeah, because we were using specific information that the phi 2,1 hat having distortion exactly equal to 2 pi over 3. And phi 2,1 hat is something already we proved easily, having distortion exact 2 pi over 3. Well,
right, but you could still relate the distortion of the new rotated function to the distortion of the original function.
Maybe that is true. Yeah, even though we cannot prove that that is exactly the number which is zeta 1, zeta m, but maybe we can make a relationship between the new map and the one we used instead of a phi 2,1 by using this construction. Yeah, I haven't thought about that, but I think that's possible direction. Yes.
Any more questions? Well, if not, thanks so much, Sunhyuk, and thanks to all the audience members. So we actually won't be meeting again in 2 weeks. There will be an AATRN poster session, but we'll be meeting again a month from now. So hope to see many of you then.
Thank you. Bye.